Well, this is our problem. A box barge 25-meter long, 4-meter wide, floats in fresh water at a draft of 1.2 meter and has an empty mid-length compartment. That means the compartment lying in the midship, whose length is 5 meters. The bottom of the barge is lined with teak. It's a wood, of course. Relative density 0.805 and 120 millimeter thick. After grounding, all the teak is torn off as if it has been damaged, and the center compartment is laid open to the sea. That means there is flooding in the midship compartment. We are supposed to calculate the final drafts. Okay, it is natural that a ship will sink down in the water by a certain amount, and it has been asked to determine the final drafts. Now we have to utilize concepts regarding the change in mean draft due to bilging of an amidship compartment. Bilging refers to a phenomena where there is any underwater damage followed by flooding. Okay, so I am going to first discuss the concept of the same here. Okay, yes, let's say there is water line and there is a box shaped barge. It is having an amidship compartment of certain length. Okay, I will also be showing the dimensions, all the dimensions. Initially the box barge is displacing a volume which you may very well notice has been highlighted with blue, and the compartment has been damaged as if there is now flooding of the water inside. So this flooding will take place. This much water will get flooded into the compartment. Now essentially there is a loss of buoyancy and the gravitational weight will exceed over the buoyancy, which will result in sinking of ship down in the water. That essentially means the draft of the ship will get increased by certain amount, and it will be compensated by the intact volume of ship's hull. Please understand, in this case the compartment is open from bottom to top, so this is no more giving watertight integrity to the hull. Only the rest of the portion which is on both sides, okay, that is going to be intact and it is going to compensate for the loss of buoyancy. So here what I have shown with dark blue, okay, it is a volume of lost buoyancy, and what I have highlighted with the yellow color, it is the compensation given by the reserve buoyancy. We can all understand that this volume is going to be same as this yellowish volume. Whatever is the volume of lost buoyancy, same will be compensated by the reserve buoyancy. That's what it has happened here. The ship will continue to sink by the time it floats on a new draft where the additional amount of water displaced, or you better say additional amount of volume of water displaced, is same as the volume of lost buoyancy. These are the dimensions. Let's say capital L, length of the barge, capital B, breadth of the barge, T1 is initial draft, and T2 is new draft. Okay, and small l is the length of that amidship compartment. So what I just mentioned, that there is an increase in the mean draft. You may very well notice dt. Dt is the change in mean draft. That's what we are interested in. As I told you earlier that this yellowish volume in total will be equals to this dark blue color, dark blue volume, basically the volume of lost buoyancy. Let's say it is small v. This volume is, let's say, small v, and I have used the respective color codes for the purpose of giving you better clarity about the same. Okay, so this volume, how much will that be if I multiply area of intact water plane with the change in mean draft? What I'm going to get is that volume which has compensated for the loss of buoyancy. I'm sure that you are understanding up to here.
Yes, sir.
Okay, very well. So this is the hold on, let me use another color. That would be more good. Uh, okay, purple will be good. Okay, this is the initial water plane area, the total water plane area. I am now highlighting with a purple outline here. But the center compartment is laid open to the sea as if the area of the compartment is no more contributing in the intact water plane area. So this is, let's say, small a. This area which I am now shading, okay, this is your small a. Small a, look at the formula above, it is small a. This area is small a. So when I subtract this area from the total area, the capital A is that total area, length into breadth, capital L into capital B. So if I subtract this, what I'm going to get is just the intact water plane area, the area which you can find out in the yellowish part. Okay. Yes. So this A minus A is the intact water plane area. dt is the change in mean draft. That will essentially be equals to the volume of lost buoyancy. Right from here, we can figure out dt will be equals to V upon A minus A. That means volume of lost buoyancy upon area of intact water plane. When we think of the calculations, small v can be found by multiplying small l with capital B and capital T1, where small l is the length of compartment, capital B is the breadth of that compartment and hence breadth of the ship also, and T1 is the initial draft. You can very well notice, I mean, it is just the volume of that cube. Okay, volume of cube is length into breadth into depth. So volume of this cube, which you are able to see right here. Okay, small l into B into T1. And now A minus A will be capital L into capital B. As I told you earlier, that would be the total water plane area. This whole water plane area from here to here. This will be capital L into capital B minus the shaded area, the shaded with purple na here. Okay, which I have shaded with hatch lines. So small l into capital B is giving us small a. So let us remember this for time being because these formulas are going to be utilized in this problem. Tell me if you are clear with this up to here. This is a small concept which I discussed for the purpose of letting you know that these are the formulas which we are going to use in this problem.
Sir,
Yes.
till now it's clear. The only doubt was that regarding that V, like volume, like we are not taking the T2 instead of that we took T1, right?
Okay. Look at this dark blue color. Okay. That cube. Okay. What I am talking about is, hold on, is only, wait, this volume. Can you notice this? This was the
Yes, sir. Yes,
volume
sir.
of
Sir.
water. This was the volume of water earlier displaced by the ship.
Yeah.
Clear?
Yes,
This
sir.
will be the volume of lost buoyancy. That would be small v.
Okay.
Understood?
Yes, sir. Sir. Understood.
Okay, so let us remember this for time being, and we are going to utilize this concept. Now I am taking you back on the numerical. Okay, yes. Now let us proceed. One by one, we will cover up everything. A box barge 25-meter long and 4-meter wide floats in fresh water at a draft of 1.2 meter. Let me make the diagram for you. The same box barge we have, length we have got is 25 meters, breadth we have got is 4 meters, and the draft, initial draft at which it is floating is, let's say, 1.2 meters. Okay. It has an empty mid-length compartment 5-meter long. This is that compartment which is having a length of 5 meters. Okay. The bottom of the barge is lined with a teak of relative density 0.805 and having a thickness of 120 millimeter. So this is how on the outside of ship's hull, the wooden teak has been placed. Okay. For some reasons, it has been placed there. After grounding, all the teak is torn off and the center compartment is laid open to the sea. Now imagine as if there is a grounding, and during the impact the teak is torn off and the center compartment is laid open to the sea. So there are two things which are happening here. One, the wooden teak is removing from the ship and the center compartment is being flooded with the water. So question is asking, of course, the ship will now sink down in the water by a certain amount, and question is asking us to determine the final draft. I hope now the question is clear to you.
Yes, sir.
Clear?
Yes, sir.
Now I am taking you on the solution. So we will split this problem in two parts, as I very well mentioned. One, removal of teak, and second, bilging of amidship compartment. Okay, removal of teak is similar to the removal of weight or mass from the ship. Okay, yes. Now let's say there is this damage. Look at the diagram again, and the teak has gone. Okay, now we will determine the new ship's draft after removal of the teak. Okay, now initial mass of the box barge. How can you determine that? Length into breadth into draft gives us
Density.
underwater volume.
Yes,
And
sir.
if we multiply with the density of water, what we are going to get is the mass of displaced
Mass.
water. That means mass of the box barge in tons, of course. Okay. We may say mass or we may also say weight, but both of them are to be expressed in tons. Okay, so length into breadth into draft into the density of fresh water. Okay, so length, breadth, and draft, the initial draft, of course, we know that, and density also of the fresh water we know. So the mass of box barge is 120 ton. Now, how much is the mass of teak? Very simple. I mean, it is very simple to determine length into breadth of the ship. Look at that black colored teak here. This is also cuboidal in shape. And what is the
Yes,
volume
sir.
of cuboid? Length into breadth into depth. The depth
Yes,
will be
sir.
taken as thickness of the teak. And if you multiply with the density of teak, what we are going to get is the mass of teak. So which is coming to us as 9.66 ton. Understood?
Yes, sir.
Initial mass of the box barge was in total 120 tons and the mass of teak in it was 9.66 ton. Now look at the diagram. The teak is torn off. The teak has gone. So what will be the remaining weight? What will be the remaining weight of the ship of the barge? So mass of box barge after that teak is removed will be the difference amongst both 120 minus 9.66. That means 110.34. Clear up to here?
Yes. Yes, sir.
Okay. And one thing I would like to mention here. The teak is having a density which is less than that of the water, less than that of fresh water. For your
Yes, sir.
information, 0.805 relative density is same as 0.805 density of the teak in ton per meter cube. Okay. Relative density is the density of any material with respect to the
Material
fresh water.
to freshwater. Yes.
Correct. So 0.805, if it is the relative density, it is also the value of density in ton per meter cube. That's why I have substituted it directly here.
Directly. Okay, sir.
Yes, and I got the value in tons, okay, not in kgs.
Okay, sir.
Okay.
So in
Now
case
here
if they are relating to some other like seawater or something, it will change.
it will change. Correct. It
Okay,
will
sir.
change then. Okay. Yeah. Now, this is the mass of box barge. Okay, one more thing I was mentioning. The teak was having a density less than that of water. So can we
Yes, sir.
understand overall it was helping the vessel to have some buoyancy,
Buoyancy.
right? If the teak has gone, now the buoyancy has been lost, and that's why you might have noticed the ship sank down in the water by certain amount.
Yes, sir.
In this case, we are no more, no, we are so far not considering the bilging of compartment. This sink case which you found, I'm again going to show it to you. After the damage and removal of teak, the ship sank down in the water all because there is a little loss of buoyancy because of the removal of
Buoyancy.
teak.
Yes, sir.
And let's say the ship is now floating on a new draft T1. Clear up to
Yes,
here?
sir.
Okay,
Yes, sir.
one more thing. Yeah, one more thing I would like to highlight. The initial draft T, which was 1.2 meters, was taken from bottom of the teak. But now the
Yes.
teak is no more there. You see here, it was taken from the bottom of the teak. The teak is no more here. The new
Yes.
draft, the new draft will be from the bottom shell of the ship.
Ship.
That's from here.
Yes.
Clear? No more including
Yes,
the
sir.
thickness. Understood up to here?
Yes, sir.
Yes. Okay. So now this is the remaining mass or weight of the ship in tons. Now this should be equals to the mass of water displaced. We all know that. Correct?
Yes. Yes, yes.
How to determine mass of the water displaced? Again, same formula, length into breadth into the new draft multiplied by the density of water in which the ship is floating.
Yes.
Clear now? So this
Yes, I
will
understand.
help us basically to determine new draft T1. T1. We will be able to know T1. So that's what we are going to do. We are going to equate L into B into T1 into the density of fresh water with 110.34. And solving it for T1 will help us to get 1.1034 meters as the new draft after the removal of teak. Clear now?
Okay, sir. Yes, sir.
Okay. Yes. So this is the new draft. Okay. Now let us forget about the teak. Imagine as if we have got a case where the draft is 1.1034 meters. And now we have got the bilging of compartment. We have got a flooding of the compartment. You have studied this part earlier. I hope you
Yes, sir.
remember from that slide.
Yes,
Okay.
sir.
And you remember the formula for the determination of change in mean draft?
Yeah, V by
Okay,
A minus
let
A.
us, I have intentionally shown this slide to you so that you can utilize these formulas over here. So now dt similarly will be V upon A minus A, and V, as I told you earlier, will be small l into B into T1, and the capital A, that means area of the total water plane, will be capital L into capital B, and the area of the uh, flooded compartment, the water plane area of the flooded compartment, will be small l into B.
Yes,
Okay.
sir.
So once I substitute all these parameters here, length of the compartment 5 meters, breadth of the ship 4 meters, initial draft T1. Please understand, I am now going to substitute this draft, not the original draft.
Yes, sir. New draft.
New draft, of course. The teak has gone. Okay. This is the draft the ship is floating at. So 1.1034 divided by 25 into 4 is the total water plane area, and minus 5 into 4 is the water plane area of the compartment.
Central compartment.
Yes. So this is giving us 0.27585 meters. You may express the value up to 3 digits after decimal. Okay.
Sure, sir.
Here I have shown with more accuracy, but you are supposed to give your answer only after 3
Three
digits
digits.
after the decimal. Okay.
Sure,
So
sir.
this is your increase in mean draft because of bilging. So what should be the final draft? Can you tell me? This
So
plus,
it will be adding
correct. So final
T1
draft will
plus
be this T1 draft plus this. That is giving us 1.37925 meters.